So this is lecture 1, part 3. This is the end of chapter 12. This whole video will be on colligative properties, and it goes really well with what we've been talking about solution concentrations, because there are 4 types of colligative properties, and colligative properties depend on the concentration of the solute molecules or ions in solution. It does not depend on the identity of the chemical or the solute. It depends on the concentration, this word here, concentration. And remember, from the last video, there are really 4 ways of reporting a solution's concentration. It is molarity, that's capital M. It is molality, that's the cursive M. We have the mole fraction, and we have percent mass, right? So if a colligative property depends on the concentration, then when you have a mathematical expression for the colligative property, the concentration should be a variable in that equation. So let's look at the 4 colligative properties in the equations. I've pulled them out of the chapter for you. They are vapor pressure, or the change in pressure, and that is delta P. And notice there is a concentration variable here. This is the mole fraction, okay? Then let's look at boiling point and freezing point, okay? The change in the boiling point and the change in the freezing point, it also again has a concentration variable, C of M. The book uses this C of M to stand for molality. So whenever you see this variable C sub M, you should think molality, okay? Molality. Then the last colligative property that we're going to cover here is due to osmosis. The book calls it osmotic pressure. Okay. It is represented by this pi-looking symbol. And again, notice there is a concentration variable here. The capital M is molarity. Okay. So because the property depends only on the concentration, it does not depend on the chemical identity. So really it's not so much about what the particle is, it is how many of the particles are in that solution. Okay, so that's something to keep in mind when we get to the end on ionic solutes, where ionic things become multiple particles when they dissolve. And we will get to that. So the first colligative property is called vapor pressure. In particular, when you have a solution, a phenomenon called vapor pressure lowering happens, where the total vapor pressure is going to be equal to the vapor pressure of the pure solvent minus the vapor pressure of the solution, okay? So Raoult's law says that the partial pressure of solvent due to a solvent, let's say solvent A, over a solution equals the vapor pressure of the pure solvent. So the pure solvent of A, this is missing a little symbol there, times the mole fraction of the solvent in the solution, okay? So really what it's saying is that if you had a container, I'm just going to make it a round container. I don't know why I chose a round one, but it doesn't really matter, okay? The pressure of the solvent P of A, okay, is going to be, so if you had a, let's say that you had a pure container of A, just A, okay? There's going to be some A as a vapor in the gas, and it's going to exert a certain amount of pressure on that container. If you measured the pressure, it's going to be P, A, little circle there. Okay, this is for the pure solvent. Okay. So if you have something where it's a mixture, let's say that there's A and B in solution, then there should be some B and some A as vapors, exerting a certain amount of pressure. Okay, so really the partial pressure of A, the pressure due to A, okay, the pressure due to the gas A and not gas B is going to be equal to the mole fraction times the pure solvent pressure. Okay, pure solvent pressure is something you can look up, okay, in a textbook. Oftentimes it'll be given to you in the problem. Okay, so the vapor pressure lowering is going to be equal to the pure solvent. Remember, again, this is the pure solvent, okay, times the partial pressure of the second solvent. Okay, that's going to be the change in the pressure. So this idea of partial pressure and Raoult's law can be applied, and so that allows us to do something called distillation, where we boil off a certain amount of liquid and collect that liquid, and that liquid should be pure than the previous starting solution. So if you're looking at it, you're saying that the total pressure of a solution is equal to the pressure of the pure solvent A times the mole fraction of A, plus the partial pressure of, the pressure of the pure solvent of B times the partial pressure of B. Okay, so let's say that you have an example here. You have some benzene, you have some toluene. These are two solvents. Okay, and so they're saying that you've got some benzene here, and you've got 75 milligrams, which is the pressure from benzene, and 22 milligrams, which is the pressure from toluene. And you do have more benzene than you have toluene. You have 0.7 mole fraction. So you have more, or you can think of this as 70% of the benzene and 30% of the toluene. Okay, so because you have more of the benzene, the vapor is richer in benzene than it is in toluene. Benzene is also the more volatile component, meaning that it becomes a gas more easily. Okay, so if that's the case, benzene is evaporating or vaporizing much faster than the toluene is, and that allows us to separate these two compounds if they were mixed together. So this is the setup we would do in lab if we did a distillation. And so in this flask here, you have a mixture of benzene and toluene. Okay, remember, benzene is coming off faster than the toluene, so as it travels through and it's boiling, so this is a heating mantle, so it's providing heat. Okay, and as it heats, it's going to boil, and the benzene and the toluene will travel through. But remember, in the vapor, it's mostly benzene, because benzene is more volatile. And so it goes through a fractionating column, and then it hits a cold condenser. And condensing means you go from a gas to a liquid. And so the condenser has cold water running through it, and so it cools the gas, and the gas becomes a liquid, and it drips down into this container here. And this container will be reflective of what was the composition of the gas. Since it was mostly benzene as a gas coming off, this will also be mostly benzene. This kind of experiment takes advantage of the fact that partial pressure of each of the gases depends on the volatility, and so really the more volatile compound will come off first, and so you can collect the more volatile compound first. The second and third colligative property is boiling point and freezing point. So you have something called boiling point elevation and freezing point depression. Okay, notice the word boiling point is followed by elevation. Elevation means an addition, so the temperature should get higher when you have a solution. Freezing point, notice it's depression, meaning that it should get more negative or lower when you have a solution. Okay, so if you have a pure solvent, if you have a pure solvent like water, and you add salt to it and you boil it, the boiling temperature will be greater than 100 because it's going to be elevated. And if you have water and you put salt in it, it should freeze at a lower temperature than 0 because it's going to be depressed. Okay, So the way to calculate it is the change in boiling point elevation. So this is really the change. Remember, this symbol here means change. Okay, is equal to a boiling point elevation constant. This is Kb. Okay, times, remember, C of M is the molal concentration, or what we call the molality. Remember, molality must be expressed in moles per kilogram. Okay, whereas the freezing point depression is equal to a different constant. It's called the freezing point depression constant, multiplied by, again, the molality. I would like you to write down in your notes these two, because you will use this often. Okay, these two is the the Kb and the Kf for water. Okay, that's something you're going to be using in the homework and in the quizzes, so I would ask you to write this down as you're in your notes. So in dilute solutions, Kb and Kf for water should be used. And basically what you'll notice here, and this is a phase diagram. You should have encountered phase diagrams at the end of 151. So the phase diagram basically shows you where is the change in states. So this is your freezing point. So you're going from liquid to solid here. Okay, and this is your boiling. This is you're going from liquid to a gas. So really, in a phase diagram, you have three parts. In this area here, you have what is the solid. Here you have liquid, and here you have gas. Okay, this line indicates what is the temperature at which this liquid to gas occurs. So notice, for a pure solvent, okay, the liquid to gas at 1 atmosphere happens at this temperature here. We know this is 100 degrees, right? A liquid to gas for water should be 100 degrees. Okay. Notice that when you have a solution, which is the purple line, okay, that has moved. At 1 atm, it's right here now, right? So now it is at 100 plus, right? So it has become more elevated. Okay. Notice with the freezing point, before it was here, this is 0 degrees Celsius because that's when water freezes. Notice that at 1 atm, when you have a solution, which is again the purple line, it has gotten depressed or lowered. Okay. So when you do these examples, if the book asks you what is the change in freezing point or boiling point, or what is the boiling point elevation or depression, you solve for TB or T of F. If the book asks you for what is the boiling point, notice carefully, what is the boiling point? Then they're asking you for what is the actual final boiling point. And so that is not delta T of B, because delta T of B is the change. So really, you're looking at, you've got to go 100 degrees for water plus your delta T of B. Okay? So if, let's say, your D of B ended up being 5, then your real boiling point would be 105. Same thing with what is your freezing point. If you want to solve for the freezing point, or the point at which it becomes a solid, you would have to go 0 degrees Celsius for water minus delta T of F. So let's say T of F was 5, then it would be, your freezing point would be minus 5. So let's look at an example of how we would use this colligative property. Remember, boiling point elevation and freezing point elevation is used in a way to determine the molality of a solution or mixture. So historically, in the past, it has been used to determine the molar mass of substances. We don't really do that nowadays because we have very accurate mass spectrometers. But really, this is just an example to show you how to use this equation and then how to use that to find molar mass. So they basically say that camphor melts at 179.5 degrees, and so it has an unusually large freezing point depression, constant of 40 degrees Celsius per molality. So this is your freezing point depression constant, or what we call K of F. Okay, And so you have 1.07 milligrams of an unknown compound, and it's dissolved in 78.1 milligrams of camphor. Okay, so basically, what you're saying is, if you had a solid, and this is camphor, okay, it'll freeze at or melt at 179.5. Okay, but what they're doing is they're taking the camphor and they're adding some unknown stuff to it. It's a very small amount. It's only this much, 107 milligrams. Okay, the rest of the camphor is 78.1 milligrams. So it's still mostly camphor, but this is your unknown. Okay, and now if you melt it again, this melts at a different temperature. This stuff melts at 176.0 degrees Celsius. So notice there's a difference in the melting point by adding this unknown solid. Okay, so they want to know what is the molar mass of this unknown compound that you've added. So basically, I would write down what I know. I know that TFF is the difference between the camphor melting point and the mixture melting point. That comes out to 3.5 degrees Celsius. And so I'm going to rearrange this equation to solve for the molality. Okay, so really if I divide this side by Kf, I divide this side by Kf. Okay, my Kf's cancel out. My C of M, or my molality, is equal to delta T of F divided by K of F. So I'm going to stick those two variables in there. My molality is 0.088 moles per kilogram. Okay, that I'm going to use as my conversion factor moving forward. So I'm going to convert my 78.1 milligrams into kilograms. So remember, 1 kilogram is 10 to the 6 milligrams. So really this comes out to 78.1 times 10 to the 6 kilograms of my camphor. And I'm going to take that number and plug it right here. I'm going to solve for the moles of my unknown. Remember, in my molality is my conversion factor. So really, remember, molality is moles per kilogram. Okay, so really that means I have 0.088 moles per 1 kilogram. Okay, I have this much unknown in 1 kilogram of camphor. So really this comes out to 6.9 times 10 to the minus 6 moles of my unknown compound. I'm going to plug that into my molar mass. Remember, my molar mass is grams per mole. So my mole is here. My grams are right here. I'm going to plug it in right there. I'm going to convert my milligrams to grams. That's why I have 10 to the minus 3 to do this conversion from milligrams to grams. So this comes out to 1.6 times 10 squared, or 160 grams per mole. All right. The last colligative property is called osmosis, or osmotic pressure, which is basically dependent on osmosis, which is the phenomenon of solvents to flow through a semipermeable membrane to equalize the solution concentrations on both sides. And so basically what you have here is a semipermeable membrane. This is the yellow thing here. Okay. Semipermeable means that it is permeable only to certain things. That's why it's semi-permeable and not just a permeable membrane. So notice the holes are small. In this particular case, water can swing back and forth here, no problem. They can travel back and forth. But the glucose molecules are too large. So the glucose molecules, which are these ones, cannot travel back and forth across the semipermeable membrane. So when you have two solutions of the same solvent separated by a semipermeable membrane, the solvent molecules will migrate through the membrane in both directions. So the water can migrate in both directions. However, and this is the important part, the solvent migration is faster from the solution of low concentration to the solution of high concentration. So in this particular case, it's going to flow from low concentration. So in this case, right here, there is no glucose. So this side is low concentration. And this side, it has glucose, so it is high concentration. And so water, I'm going to erase some things here. Remember, water can travel in both directions, and it is traveling in both directions, okay? But which way is the water going to travel more or higher, okay? It's going to travel from low concentration to high concentration. So more and more water is going to flow in this direction, Okay, that's always the case with the semipermeable membranes. Remember, it's always from low to high concentration. Okay, low to high concentration. So, as a result, the water will flow from the beaker through the membrane into the funnel. Okay, so notice this setup here. You've got a semipermeable membrane here. This is the yellow little piece right there. Okay, this thing is purple because it has glucose. So remember, inside the funnel is going to be what we call high concentration. Okay, outside the funnel, oops, let me just rewrite that again. Inside the funnel is high concentration. Outside the funnel is pure water. So the water here is going to be low concentration. So based on this fact, the water is going to flow, remember, in the direction of low concentration to high concentration. So remember, the water is going to flow in this direction, right? Okay. The book shows you a little blow up of it. It's going to flow in this direction. Okay. As a result of that, the water is going to push upwards in volume, and so the change or the difference in height is going to be our osmotic pressure. Okay. So let's read what it says here. The glucose solution continues to rise in the funnel stem, which is the thin piece there, until the downward pressure exerted by the solution above the membrane eventually stops the upward flow of the solvent, i.e. the water. So the osmotic pressure is a colligative property of a solution equal to the pressure that, when applied to the solution, just stops the osmosis. Okay? Now, the more glucose you have, the more osmotic pressure you will experience. Okay? So really, the osmotic pressure, and here's the mathematical formula. Osmotic pressure is equal to the molar concentration in moles per liter. Another way to say this is molarity. Okay, times the gas constant. Remember, the gas constant from back in the day when we did gas laws is 0.0821 liters atmospheres over Kelvin mole. Okay, and the temperature must be in Kelvin because the gas law has the variable K in the units. So let's look at an example. The formula for low molecular starch is C6H10 parentheses N, where N averages 200. So they're saying that this molecule strung together, with 200 of them strung together, is basically your molecular structure for starch. Okay? So really, let's first calculate the molecular mass of starch. Okay? The molar mass of starch is going to be C6H10O5 times 200, right? So it's going to be 12 times 6 for the carbon, plus 10 for the hydrogens, plus 5 times 16 for the oxygen, right? So this comes out to, let me do that calculation real fast. This comes out to 162. Okay. And remember, there are 200 of these fragments strung together, so you got to multiply that by 200. So this comes out to 32,400 grams per mole. Yes, starch has a huge molar mass. Okay. So it's saying that you have 0.79 grams of starch and it's dissolved in 100 mils of water. Okay, and what is the osmotic pressure at 25 degrees? So really, we need to know the osmotic pressure. To do that, we need to calculate that. We need to know the molarity, which is really in moles per liter. We need to know R, which is your gas constant, which we already know. 0.0821 liters atmospheres over K mole. And we need to know the temperature in Kelvin. The temperature in Kelvin is going to be your 25 degrees Celsius plus 273 to convert it to Kelvin, which is 298 Kelvin. last but not least, you need to know the moles and the liters, right? Because you need to plug it into your molarity. Because we don't know what this is yet, we need to calculate this, okay? So the moles is going to be converted from your 0.798 grams, and we're going to convert from grams to mole. And again, we're going to use the molar mass calculated above, 32,400. This comes out to 2.46 times 10 to the minus 5 moles of starch. Okay? Then your liters is going to be, I'm going to write it here a little bit lower, 100 mils. And if you convert that 10 to the third mils into 1 liter, or 1,000 mils is 1 liter, this comes out to 0.1000 liters. Okay? If you plug these two numbers into your moles and your liters, you've got your 2.46 times 10 to the minus 5 moles. And you've got your 0.100 liters. So this comes out to 2.46 times 10 to the minus 4 moles per liter. Now that you've got all of these things figured out, you have your molarity, your R, and your T, you're just going to plug it into your osmotic pressure equation, your molarity, your gas constant, and I'm just going to write it here, so but you know that it's multiplied so that it doesn't quite fit, and your temperature. Okay, notice your Kelvin cancels out, your moles and your liters cancels out. You are left with atmospheres, which is what is the correct unit for osmotic pressure, because ATM is a pressure unit. So let's just finish up. Sorry, that slide jumped a little bit. So the osmotic pressure is going to be equal to, if you do all the calculations through, it's going to be equal to 6.02 times 10 to the minus 3 atmospheres. Okay, and if you would like to, and the book wants you to convert it to millimeters of mercury. So you're going to multiply 1 ATM is 760 millimeters of mercury. This is just the normal conversion factor for pressure. So this comes out to 4.58 millimeters of mercury. Okay. In a lot of times you will have to do this to use any of these equations. You're going to have to calculate the concentration in the correct expression, whether it's molarity or mole fraction or molality. Okay, and that's exactly what we did here. We calculated the molarity and then we plugged it into the equation. So really, osmosis or cellular osmosis is kind of cool because if you think about it, a cell is basically an aqueous solution enclosed by a semi-permeable membrane, right? Your cell wall is semi-permeable. Water goes in and out, no problem, but things like fats and salts and things like that cannot pass through that cell membrane without some kind of, encouragement either from like a sodium pump, etc. So really that cell wall is a semi-permeable membrane, and so the solution surrounding the cell must have an osmotic pressure equal to that within the cell. And so we have three kinds of situations that a cell can be in. Hypertonic, meaning that there is a higher concentration of the solution outside the cell. So in this case, this is a higher concentration outside the cell, and inside the cell is a lower concentration. Okay, an isotonic solution wherein the concentrations are equal inside and outside the cell. Okay, and a hypotonic situation where there is a higher concentration inside the cell and therefore a lower concentration outside the cell. So you can see three pictures, and this is pictures of a real red blood cell. So this is what we call a hypertonic solution, where you have a higher concentration outside the cell, and as a result, the water flows out of the cell. Remember, from lower concentration to higher concentration. So the cell shrinks, So therefore, the osmotic pressure of the solution is greater than the osmotic pressure inside the cell. You have an isotonic solution here in the middle, where your your osmotic pressure of the solution equals that of the cell. And here you have a hypotonic solution, where the osmotic pressure of the solution is less than that of the cell. Why? Because the water is flowing in from lower pressure to higher, lower concentration to higher concentration. So the water is going to flow into the cell, and as the water flows into the cell will swell and get really, really big. You can actually do an experiment at home. This is a very simple experiment to do and fun to do with the kids. You can put an egg. An egg is basically one large cell. And so basically you can put it in a solution of vinegar to dissolve the calcium eggshell outside. And so once you do that, you leave it overnight and then you pull it out the next day and wash it off. You'll notice that your egg basically has a very, very thin white coating around it, and that thin white coating is your semipermeable membrane, okay? That's your cell membrane for the egg, okay? Now you should do this with a raw egg, not a cooked egg, right? You need a solution inside the egg, so you need a raw egg. You put that raw egg that you've now removed the eggshell from, and you put it in water. Remember, water is pure water, and so it has no solutes in it, so it's very, very low concentration. And so you put that egg in the water and it'll swell because it's a hypotonic solution. The water is going to rush into the egg to try and dilute out the fats and the salts and things in the egg. If you put it in pure water, after a couple of hours, the egg will get really swollen. Then you put it in corn syrup. Corn syrup is basically very little water and mostly glucose. It's going to be a hypertonic solution, and all the water is going to rush out of the egg to dilute out the glucose, and it's going to get really, really small. And you can wash it off and go back and forth and do it again and again and again. Small egg, big egg, small egg, big egg. Something fun to do with the kids. It does take a little bit of time for the water to rush in or to rush out of the cell, so you need to leave the egg in there for a couple of hours to see the effect. So the last thing to keep in mind is that with all of these colligative properties we've been talking about so far, and with all of these equations, we've been talking about covalent compounds, compounds that do not separate or disassociate when dissolved in water. So normally if you have something like glucose and you throw it into water, glucose is C6H12O6, okay? You throw it into some water, okay, you'll get glucose, and it's not going to separate, right? Each one of these things is glucose, okay? But if you have something like NaCl, okay, when you put it into water, it's not going to be NaCl in water. It's going to be Na plus in water, Cl minus in water, right? Okay. So for every one particle, you actually get two particles, right? Because it separates into two ions, right? So you have to keep this in mind because remember, colligative properties depend on the concentration of the particles. So you've actually doubled the concentration by dissolving it in water, or you've actually not doubled the concentration, you doubled the number of particles, thereby doubling the concentration. So to keep that to keep track of that, what we do is we add a variable called I to every one of these colligative property expressions, where I stands for the number of ions, the number of particles, okay? And so each separate ion is considered as a particle, okay? So if you have NaCl, your I would be equal to 2, okay? If you have something like KSO4, remember your polyatomics, SO4 does not dissociate into more things. It stays together as SO4. So you end up with 2 K pluses and 1 SO4 2 minus, or sulfate. So 2 plus 1 is 3, so I equals 3. Aluminum sulfate, you'll get 2 aluminums and 3 sulfates. So 2 plus 3 is 5. Okay? It's something to keep in mind. As you're doing this, when you're doing your homework, when you're doing your quizzes and exams, If you notice that the compound is ionic, you must keep track of that and stick I into your equation. In fact, if I were you, I would just write these 4 equations in your notes for colligative properties. You can write it on your periodic table so that you have it with you when you're doing your quizzes and your exams. So let's look at an example. It asks you to estimate the freezing point of a 0.01 mole per kilogram. Remember, this is a molality, which is moles per kilogram, okay, of aluminum sulfate, and they give you the aluminum sulfate, and they ask you to assume the value of I based on the formula of the compound. So basically you're saying this is 2 aluminums, 3 sulfates, so 2 plus 3 is 5, so I equals 5, right? Okay. So let's write down what we know. We know I equals 5. Kf for water, because they want to know the freezing point, right? So we have to calculate delta T of F, okay? So K of F, if you look at the table that we looked at before, let's just slide back so you know which table I'm talking about. If you're looking at this table here, okay, the Kf is 1.858, so let's just slide back. 1.858 is where I got that from, so I'm going to round it to 1.86 degrees Celsius divided by molality, and the molality is 0.010 moles per kilogram. So I'm just going to plug in all of these things, 5, my K of F, my C of M, or my molality, and I get 0.093 as my freezing point depression. Okay, so this is what we call a freezing point depression. Okay, but be careful. In this problem, it actually asks us to what is to estimate the freezing point itself. Okay, so remember that the freezing point of water is 0 degrees Celsius, right? So therefore, because it's depressed by 0.093 degrees Celsius, your new freezing point is going to be negative 0.093 degrees Celsius. Okay? This is why we throw salt on the roads when it's really cold in certain parts. Like, I was just watching this show about, heavy truckers and things like that. And so, up in Canada, what they do is they salt the roads, right? Because normally water will freeze at 0 degrees. But if you throw salt on the roads, what will end up happening is that the water won't freeze at 0 degrees. It'll freeze at like negative 10 degrees. So as the temperature drops, the roads won't ice over. Or will it ice over, but it'll ice over at a much lower temperature than it would if it was just pure water. Freezing point depression is cool. The boiling point elevation is also another thing that we observe. If we have some water, we throw some salt in it, the water will boil at a temperature higher than 100 degrees. And that's part of the reason why this is not the only reason, but part of the reason why we throw salt in water. We're trying to boil water for noodles and things like that. So anyway, these are just some kind of applications. So this ends this video. I would like you to now work on your homework from your homework booklet. You will need to do the homework and do all of the homework from chapter 12. That's been assigned to you in the booklet, and you just start from the first page where it says chapter 12 homework and go all the way until you see chapter 13 and stop. Okay, and you will have on Canvas a place where you can upload the homework. So again, you should scan with your smartphone or your tablet all the pages into one file and then put it in the Dropbox, and then from Dropbox you can just submit it onto Canvas. If you don't know how to do this, you should watch the video that is on the front page of Canvas when you log into this class. With the homework, it is a written assignment, so you make sure your units are clear, okay? And upper and lower case must be differentiated. For example, if you have molarity, you should have capital M. If you have molality, you should have the cursive lowercase m. In fact, I would suggest you write your molality like this, okay? If I can't tell the difference, then I'm going to mark it as incorrect. You must clearly indicate if you're calculating liters of solution or mass of a solution or the mass of the solvent, etc. I highly advise you to do this or you will get confused. You're going to go, wait, was that the mass of the solution that was total? Or was that the mass of the water that was the solvent? That makes a difference, okay? Remember to use know and solve. I do think this will make life easier for you. And last but not least, try and put all your final answers in a box. I want all the final answers in a box with the correct units and the correct significant figures so that I know that that is your final answer. Otherwise, when I'm trying to grade your homework, you're scribbling all over the place and I don't even know which one is your final answer. So remember, work neatly and work carefully with your units. If you ever have problems with your homework, I'm here to help you. We want to get through this semester together. I really suggest you can find me on, text me on the GroupMe app, and we can set up an appointment. We can meet on Zoom so that we can I can help you if you ever have any problems, okay? I don't want you to struggle on your own with the homework. You shouldn't be sitting there for hours and hours looking at one problem. That doesn't make any sense to me. I think you should just reach out for help. I'm here to help you. I really am here to, and I wish that all of us would get through this semester and, do wonderful and do well. So don't be afraid to reach out to me. I'm here to help you. All right. I would also suggest once you finish the homework, you work on the quiz. For Chapter 12, there is a quiz that corresponds to this material from Chapter 12, and that will prepare you for the exam that will be coming up in a couple of weeks. Alrighty, that ends this video, and I will see you in Lecture 2.